Hello student, I am Dr.A.K Sinha, Professor of Chemistry. Today I am going to discuss colligative properties and determination of molar mass. Colligative properties and determination of molar mass. Last class I have discussed ideal and non-ideal solution. In a non-ideal solution, main things I have discussed that two plots I told you, means in one there was a positive deviation in one plot, in other negative deviation from Rod's law. Rod's law is a standard. Then in one case there was positive deviation, means vapor pressure curve was upside, and in negative deviation vapor pressure curve was down, means in comparison to the Rod's law, positive deviation means that curve went up in a non-ideal condition, and in negative deviation curve went down in comparison to the this Rod's law. Then Rod's law is a standard. Then Rod's law, according to the Rod's law, what should be here in non-ideal solution, different is there. Means actually in one case it was positive, other case it was negative deviation, and both it is shown in a diagram. Okay, one by the dark line, other by the dot. Okay, then here just main things I will brief you, then I will come to the colligative properties. That why it is positive, why negative, this is very important, already discussed, but again I will brief you so that you can remember it. Then actually when two component you are mixing, solvent and solvent, then suppose one component is A and other component is B. All are A first component, suppose it is A, many molecules of A will be there, and B also many molecules of B will be there. Then here in a very simple way what will happen, that A molecules interaction, they can do interaction with B molecules. A and B both can do. Okay, but what will happen, that if A and B are, their interaction is very less interaction, then what will happen, that most of the AA and BB are free. They can come to the vapor stage, come to the vapor phase. Then its pressure will increase, because very less A and B are interacting. Most of them are, or you can say interaction is very less interaction. Then A molecules and B molecules both are free, it can come to the vapor phase. That's why pressure will increase, vapor pressure will increase. It will go positive, more than Rod's law. Rod's law expecting more than that. Okay, positive deviation. And in negative deviation, because here A molecules and B molecules, AA molecules and BB molecules, they are interaction is more. Then when interaction is more, then less number of molecules will go in the vapor phase. Then if less number of molecules will go in the vapor phase, then less vapor pressure. What was expecting Rod's law? Less than that. This is called negative deviation. And one more thing, that why it is curve? Why not a straight line like that? Then here answer you can, as you will see that already diagram I have sent, then curve is there. Then for the curve reasoning, I am telling you, either for negative or positive, it will apply for both. Then because if vapor is more, then vapor is more, then it is increasing. Suppose positive, I am talking about first positive. If vapor will reach to the vapor phase slowly and slowly, then it's a mole fraction. You know that mole fraction and vapor pressure both are related. Then vapor will start going slowly and slowly, and with the time more and more vapor will reach, then more and more pressure will, it will create more and more pressure. After when it will maximum vapor will reach in vapor phase, then that time curve will be more high. Okay, then slowly and slowly it will start from 0 0 0 and it will little slowly and slowly it will increase, and maximum it will go, okay. And after that, when maximum vapor reached to the vapor phase, then with the time less molecules are there to reach to the vapor phase. That's why it will begin to come down. That is the reason why it is showing curve. Now this is the positive. Negative, same reasoning, that because most of the molecules are interacting, hence they are not free to go to the vapor phase, then less molecules will go to the vapor. Then again it will start with the 0, that it will start going from 0, and in this case in the beginning, whatever you can say free was there, free molecules, they will go to the vapor phase. That after that it will because now molecules are less to go to the vapor phase, then it will begin to come, you can say, down. In the beginning maximum molecules went, and after that slowly and slowly with time it began to decrease because molecules are less. Then it will come down. In the beginning it was more, after that slowly and slowly it will begin to come down, and when it will be very less molecules are reaching, then maximum down it will go, and after that what will happen, maximum down it will come, and after that what will happen, that it will because minimum it reached to the whatever molecules was there, and with the time in the beginning it was more, after that it was becoming slowly and slowly less molecules are going there, then vapor pressure will be less, correct. Then in the end actually some molecules you can say they may go fast, because now you can say all vapor, maximum vapor this thing whatever there, in the beginning it was more, and then slowly and slowly began to become less and less, and after that only few molecules may be left, then their speed may be more, then whatever was remaining that will go fast, then again it will very little it will increase, then it will show curve, it will show negative deviation from Raoult's law. Okay, Raoult's law, just a straight line curve deviation, from that it will go down, correct. The why it is going up, why it is going down, and why it is the only in curve, why not in a straight line, reasoning I told you. Now I am going to discuss colligative properties and determination of molar mass. Actually, you know that colligative properties, here first I will tell the meaning of colligative properties. It is a Latin word, co means together, and colligative. Then co you remove, then ligative it is remaining. Then ligative word came from ligare, Ligare, R-E, Ligare, ligare. Then ligare means to bind. Ligare means to bind. Okay, bind, bind. Then colligative properties. Colligative means it is related to binding together. Binding together. That is the meaning of colligative. Then now binding is there. When then what type of binding? How binding may be a strong, weak, then but its meaning is there. Molecules will come close to each other. Coming close to each other means just like a interaction. Then it will tell about the interaction colligative properties. There are 4 colligative properties. First property is a relative lowering of vapor pressure of the solvent. Relative lowering of vapor pressure of the solvent. Second is depression of freezing point of the solvent. Third, elevation of boiling point. Elevation of boiling point of the solvent. Elevation, ELEVATION. Elevation of boiling point of the solvent. And fourth one is last, osmotic pressure of the solution. Osmotic pressure of the solution. Then here I want to tell you that in 3 cases we have seen they have used as for example relative lowering of vapor pressure of the solvent. They have used the word solvent. Depression of freezing point of the solvent. And third also elevation of boiling point of the solvent. But in osmotic pressure, in case of osmotic pressure of the solution. Then 3 have solvent used. Why solvent? Then you know that in 2 component, here we are using 2 component binary solution, and solute is non-volatile. Don't forget, in all 4 cases we are using solute. Solute is non-volatile. Okay, then here you know that if you will take pure solvent, then its vapor pressure will be more. Already I discussed previous class. Pure solvent, because nothing, only one type of is there, other component is not there, then they are free. They are from the surface of molecules of solvent molecule, they are free to go to the vapor phase. Then maximum whatever is possibilities, it is going, and they are making a equilibrium, liquid and vapor phase equilibrium. Then that vapor is creating, if you take in a closed vessel, then that vapor will create pressure on the surface of liquid. Okay, both are solvent only, one are the free, molecules are free. Okay, that went up, that is the vapor phase and liquid phase. Then vapor will create pressure on the liquid phase, then that pressure is called vapor pressure. Then in pure solvent, vapor pressure is maximum. Okay, for any solvent, maximum. But only in the, as for example, water. If you have not added anything, then it is a pure solvent. It's like distilled water, that nothing is there. And that is the pure solvent. Benzene, pure solvent. Carbon tetrachloride, CCl4, benzene, you have not mixed anything. Many solvents are there, organic but water is universal solvent. Then they have a maximum vapor pressure. Now suppose water. In water now you are adding solute. Then now this solute blocks the path of the vapor. Molecules which were going to the vapor phase, now this will block their path. They will come in the front of solvent molecules, and less vapor molecules will go to the vapor phase. Hence, when less vapors are going, less molecules of vapor molecules are less, then they will create less vapor pressure. Then now it becomes solution, because solute you have mixed. Solute you have mixed in the solvent, in water. You have shaked. Now it is a solution. Then in solution, vapor, for the vapor pressure only solvent is required. Only solvent is responsible. Because their molecules are coming in, because it is a solute is non-volatile. It is simply creating problem. Because they have dissolved and came on the, you can say, surface of liquid, upper surface of the liquid. And now it is creating problem for this water molecules which were going upside, now it is going less. Hence solution has less vapor pressure. This concept is very, very important. In everywhere this concept you will use. Okay. Then now this I have main things I have told you, that solution has less vapor pressure and pure solvent has more vapor pressure, maximum. Hence this you will take the difference, how much decrease the vapor pressure, and that is called delta. Delta, a small triangle like that. P means pressure, a small p means pressure. Okay. Then delta P is equal to, suppose pure solvent was having a P-1IITJEE, we can write P-1IITJEE. 1 means pure solvent, 1 means one component. 1 means one component, and 2 means second component, P1, P2 like that. Vapor. Then here P-1IITJEE is for pure solvent, vapor pressure of pure solvent. Correct? Then in the beginning pure solvent was having, suppose 1000, just simply 1000 unit, 1000 atmospheric pressure or bar anything. And after mixing it became solution, then solution is a less pressure. Suppose now it became 600 bar or atmospheric pressure. Then 400 differences, then delta P is equal to what? P1 difference of both high pressure minus low pressure. Correct? Then this P1 naught 0 you are writing a subscript, then P1 naught minus solution pressure, that is called delta P, change in vapor pressure. This concept is very, very important, and this difference of pressure, vapor pressure, due to that all four what I told colligative properties depend in this only in this. Every time you will use this. Okay. Then this is the mathematical, actually in mind you can calculate. It is not very long. Concept is very, very important. Okay. Then now I am telling you in a mathematical way also. Derivation you can tell, easy derivation if you will understand. And I think because main things you are knowing, and quickly you will understand, and in mind also you can think and you can understand. Okay, it is not very difficult, because concept you are knowing, that's why it is easy. Then now only you have to suppose some terms. Then now I am going to derive the expression. Okay, expression deriving means it is very, very helpful for you in solving the numericals. Okay, because nowadays objective type questions will be there. Then only in subjective, where subjective type questions are asking, university or council examination or university examination they will ask. Board examination they can ask for 12th. Then there you have to derive also. That time also it will be helpful. But for solving numericals for IIT or medical or any other examination, then these concepts are each step concept is, each step of derivation is important, because there you will require in all steps you will utilize in solving the numericals. And now I am going to derivation is just for namesake only, not very difficult, easily you can understand. Then here I am going to tell you vapor pressure. Already I have discussed vapor pressure of a solvent in solution. Vapor pressure of solvent in solution is less. Vapor pressure of a solvent in solution is less than that of a pure solvent. Pure solvent has more vapor pressure, and same solvent when it is in a solution form, then that time its pressure will be less. Okay, because in solution solvent is also there. Then when it will be in the form of solution, solvent plus solute, that is equal to solution. Then when it will be in the form of solution, then that time solvent pressure will be less, and pure solvent has pressure more. This is a very, very important thing, already you know. Now what will happen, this change or decrease in this pressure, due to this vapor pressure of solvent, pure solvent is more, and vapor pressure of solvent in solution is less. This results, or you can say result of this established that the lowering of this is called actually lowering of vapor pressure. Vapor pressure decrease, then this result established that the lowering of vapor pressure depends only on the concentration of the solute particle, and it is independent of their identity. Which type of particle is there, it does not depend. Okay, then this because vapor pressure decreased, pure solvent was more, and that solvent only, when you will put some solute, it becomes solution, that time pressure decreased. Vapor pressure of solvent in solution will be less. Then because pressure decreased, that's why it is called vapor pressure decreased due to the solute, and that's why it is called lowering of vapor pressure. Lowering, LOWER, lowering of vapor pressure. That lowering of vapor pressure is established. These important things I told you. Then now you know these things, equation, you know that relation between vapor pressure and mole fraction, that relation you know, that P1 is directly proportional to X1. 1 means always component 1. Then here same things, same equation you have to recall. Okay, that vapor pressure of the solution and mole fraction. 3 things always remember now: vapor pressure of the solution, mole fraction, and vapor pressure of solvent. Then you know that P1 is directly proportional to M1, a small m1, mole fraction. And if you will equate it with equal, remove the proportionality sign, then you will get P1, already you know, P1 is equal to P1 naught into M1 into X1. Mole fraction X you are using. Okay, X1 you write, X1, a small x1. Then P1 is directly proportional to X1, mole fraction. And in term of equality, you have to multiply with a constant. That constant is actually P1 not 0. Then now this P1 is equal to P1 not 0 into X1, where P1 not 0 is the, you can say, vapor pressure of pure solvent, vapor pressure of pure solvent. And this P1 is for vapor pressure of solution. Okay, vapor pressure of solution. Then now you got this relation, that is the P1 is equal to x1 x1 into P1 0, or you can tell P1 0 into x1. Okay, that is the same things. This relation is important relation. P1 is equal to P1 naught into x1. Now what you have to do, x1 value you have to find out, and delta P value already concept I told you, delta P lowering. The reduction of vapor pressure, the reduction in the vapor pressure of solvent, that is the delta P1, that is the delta P1. The reduction of the vapor pressure of solvent, that is called delta P1, is given as delta P1 is equal to, you know, P1 naught. P1 is vapor pressure of pure solvent is more, highest. Then P1 naught minus P1, correct? Both are vapor pressure of solvent only. One is of pure solvent, other is for impure solvent. After adding the solute, after the adding solute becomes solution, in that solution solvent is there. Then now it is decreased due to the solute. That time its pressure is P1, and pure solvent pressure was P1 0. Then P1 0 minus P1, that is equal to delta P1. Then now this delta P1, here value if you will put this thing, delta P1, you know that P1 naught minus P1, that is equal to, that actually now P1 value you have to put here. In this equation, delta P1 means lowering of vapor pressure. Delta P1 is equal to P1 naught minus P1, and minus P1 is equal to, already you have written, P1 is equal to x1 into P1 naught, but that is a mole fraction into this vapor pressure, standard vapor pressure, means pure vapor pressure of the solvent, P1 naught, pure vapor pressure of pure solvent. That already in the beginning, this relation P1 value you put here. Then P1 is equal to x1 into P1 naught. Then now it became what? Already P1 0 was there, and now minus P1. Then minus P1 value you have put, that is the x1 into P1. Then now it became P1 naught 0 minus 2 times P1 naught came, because P1 is equal to x1 into P1 naught. Okay. Then now after putting the value, you will get P1 naught 0 minus again P1 naught 0 x1 from the first equation, means what in the beginning I told you. Then now 2 P1 naught is there. Then now you can take common P1 naught 0 minus P1 naught 0 into x1. This is mole fraction. Then P1 you can take a common. Then what you will get? Then P1 you have taken common, then in bracket 1 minus x1. Then now you are knowing 1 minus x1. Then 1 minus x1 is the mole fraction of one component, first component. Then what is the mole fraction of second component? Then that will be 1 minus x1, because mole fraction of one component and other component is equal to 1. x1 plus x2, that is equal to 1. Then now 1 minus x1, that is the x2 equal to x2. Then now 1 minus, in the place of 1 minus x1, you can write x2. Then you will get, what you will get, delta P1 is equal to, delta P1 is equal to P1 naught or P1 0 into x2 into x2. This you got. That is the second important relation. That is that delta P1 is equal to x2 into P1 naught. x2 is equal to x2 into P1 naught. This is the important relation. Okay, first relation I told, that time at the beginning I told you P1 is equal to x1 into P1 naught. Now in delta P you have put the value of P1, then now you are getting delta P is equal to x2 into P1 naught, because 1 minus x1 is equal to x2. Then many things now you have written. After that, when this delta P1 is equal to x2 into P1 naught, then what is the value of x2? Means a mole fraction of x2. This is actually, this is for this things, mole fraction of solute. x2 means solute. Okay. Then now here x2 value is equal to what? Then delta P1 divided by P1 naught 0. Very simply, delta P is equal to x2 minus P1 naught. Then what is the value of x2? Then x2 is equal to delta P1 divided by P1 naught. Correct? Then now this actually delta P divided by P1 naught, this is the relative. This delta P value in comparison to the pure solvent, how much, in comparison to the pure solvent, how much change took place? I told you 1000 minus 600, that is 400. Then that you are talking about 400 divided by 1000. This ratio you are, that is the relative. That the word relative is coming from here. Then here delta P1 divided by P1 0. That is the relative vapor pressure. That value is equal to x2. That value x2 is equal to this delta P1 divided by P1 naught. Then now if you will put the value of delta P1, then delta P1 means what? P1 naught minus P1. P1 naught means P1 0. Upside subscript 0, a standard, means pure vapor pressure of pure solvent. Then P1, delta P value is the difference of two pressure, P1 naught minus P1. And down already P1 0 is there. That is equal to x2. That is actually called a relative lowering of vapor pressure. You have derived the relation. It means ratio is the relative lowering of vapor pressure. Correct? Now in a solution, just to understand, in a solution containing several non-volatile solute, the lowering of the vapor pressure depends on the sum of the mole fraction of different solutes. Okay. Then means suppose sometimes in many solids may be dissolved in the solvent. Then you have to all mole fraction. Even you are considering only solute and solvent. Then total you already know, total always will make sum of all. Okay. How many you can say components are there? In total, mole fraction of all you have to consider in total. But here only two are there, mole fraction of solute, mole fraction of solvent. Then this I told you that delta P upon P, delta P upon P1 naught, that is equal to X2. This is the relative lowering of vapor pressure, and delta P1 value if you put, then P1 naught 0 minus P1. Okay, that value we keep upside only. Then now it will become P1 naught minus P1 naught minus P1 divided by P1 naught, that is equal to X2. Now here again, now we have to use mathematics. Chemistry is up to here only. Actually, in chemistry, physics, chemistry, math, all are interrelated. You can't separate. Now here mathematics you have to apply. What mathematics you will apply here? Then okay, that I will tell you, and the end I will tell you that what I want to tell you. First to understand just other things important related to here, that experiment this expression what I have derived, the expression on the left hand side of the equation what I have derived in that, that is the P1 naught minus P1 divided by P1 naught, that is equal to X2. This is actually called relative lowering of vapor pressure and is equal to the mole fraction of solute. X2 is equal to solute, X1 is equal to solvent. 2 means 1 is for solvent and 2 is for solute. Then now that this relation I told you is the relative lowering of vapor pressure, main expression, this only. Now, but you can keep the value of X2. Then what is the value of X2? Then in terms of moles, mole fraction of solute is equal to what? Number of solute divided by total number of solute and solvent, that you know, means N1 divided by N1 plus N2, correct? N1, but here solute you are considering, for X2 value want to write here, then N2 you should write, number of moles of solute. 2 term you are using, okay, 2 is for solute, then N2 divided by N1 plus N2, that value you can write. Then you will get that P1 naught minus P1 divided by P0, that is called X2, and X2 is equal to N2 divided by N1 plus N2. Okay. Now here again you already this concept I discussed in this next what I want to tell you, that this here N1 and N2 are the number of moles of solvent and solute respectively present in the solution. For dilute solution, now this concept I am telling already discussed in details. For dilute solution, N2 can be neglected. N2 is very, very less than N1, means in comparison to the solvent, solute is very, very less if solution is dilute. Here I want to tell you, colligative properties is only for dilute solution, not for concentrated. In concentrated solution it will not work. Properties of dilute solution. This is also another term is there for this chapter. You are telling colligative properties. Then other way also you can tell properties of dilute solution. Another topic. I mean same things. You can tell in the place of colligative properties of dilute solutions. Then colligative properties is always for dilute solution. Whenever you can say both term will come together, number of moles of solute and number of moles of solvent, then in respect of solvent, solute will be very, very less, hence you can neglect it. Then N1 plus N2 was there. Then now it will be approximately, sign of approximate you can write, that is equal to only N2, N1 solvent, only solvent, because solvent is very less. Then N1 plus, in the place of N1 plus N2, that is approximately equal to N1 only, means a solvent. Solvent is very less. Then now you can see upside was, this was the mole fraction was N2 divided by N1 plus N2. Then now down in you can say denominator, down you can write only N1. Then now it will come upside, numerator only N2 and down only N1, N2 divided by N1. This concept I have discussed earlier classes. Then now here relative lowering of vapor pressure is equal to N2 divided by N1. Then now again you can use mathematics here. Here I am telling you, just you can N2 and N1 and N2 value you have to put. Formula you know. That N2 means number of moles of solute. Then that formula you know, mass of solute divided by molecular mass. Mass of solute divided by molecular mass, that is the number of mole. Then N2 is equal to number of mole. Then here in the place of N2, now you can write mass divided by molecular mass, mass of solute divided by molecular mass of solvent. Then W2 you can write as a mass of solute, and M2, capital M, you can write for mass of solvent, mass of molecular mass of solute. W2 is a mass of solute in gram, and M2 is equal to molecular mass, capital M2 is equal to molecular mass in gram. Correct? This formula you know. Then here in the place of N2 you will write W2 divided by M2, and N1 same way, N1 number of moles of solvent, same way, mass divided by molecular mass. Correct? Then that also you can write same way, N1 divided by this W1 divided by N1. W1 is the mass of solvent, and this M1 was, and M1 is, you can tell M1 is molecular mass of solvent. Then in the place of N2, right, in the place of N2 you have written W2 divided by M2, and N1 down N1 is there. Then N1 is equal to W1 divided by M1, and just to reverse it, then you will get the final relation in terms of molecular mass. You will get now relative lowering of vapor pressure is equal to relative lowering of vapor pressure, means P1 naught minus P1 divided by P1 naught. This is called relative lowering of vapor pressure. Then relative lowering of vapor pressure is equal to, now you can tell, W2 divided by M2. Now denominator, that term you reverse it, then you will get M1 will go upside, down will be W1. Then this is the final, you can say, expression. Relative lowering of vapor pressure is equal to W2 in a numerator it is a W2 into M1, and down M2 into W1. You can easily you can do all the thing, not a problem. Okay, then this is the final expression, and here W1 and W2 are the masses, and M1 and M2 are the molecular masses or molar masses of the solvent and solute respectively. Okay, hence now out of this relative lowering vapor pressure is equal to, now I told you, W2 into M1 divided by M2 into W1 you got. And now you want to calculate the lowering of vapor pressure, then these four values you should know. You should know if pressure, to pressure you are knowing, that is this pure solvent pressure you are knowing, and in solution what is the pressure of solvent you are knowing. Then now this lowering of vapor pressure will come to know, and this side out of four term, any one you want to calculate. Generally molecular mass of solute is asked to calculate molecular mass of solute, because if you will come to know the molecular mass of solute, then what is the name of solute, you can understand the which type of compound was there, because molecular mass is fixed. For any molecular mass is fixed, hence you can get idea. Then this I have told you important expression. One thing actually I wanted to tell you, because in sometimes this concept somewhere may be written in other books or other places. Here that when you have written relative lowering of vapor pressure, P1 naught minus P1 divided by P1 naught, relative lowering of vapor pressure. This also you can write, because down P1 naught is there in denominator, P1 naught is there, and upside in numerator is what is there? Numerator it is the P1 naught minus P1. Then down P1 naught is there. Then if you want to separate both, then you can write same things. You write P1 naught divided by P1 naught minus P1 divided by P1 naught, means you can bifurcate. Then P1 naught will cancel. Then you will get 1 minus P1 divided by P1 naught. This term also you can write. Okay, this is only nothing, is just like a mathematics. In that way also lowering of vapor pressure you can write in this way also, because in up and down both P1 is there, P1 naught is there, upside also, down also. Hence if you want to separate it, you can separate it. P1 naught divided by P1 naught minus P1 divided by P1 naught. P1 naught will be cancelled. Then it will become 1. Then 1 minus P1 divided by P1 naught. That is the relative lowering of vapor pressure. You can write in this way also. And this is equal to N2 divided by N1. And N2 value you can put, N1 value you put. Then means this is another way to tell the lowering of vapor pressure. Then now this I have discussed. Now I am going to you can say numerical. One numericals is there. I will tell you. Usually now you can solve. Here what will happen? All values they have given. Molecular mass of the solute you have to calculate. Molecular mass of solute you have to calculate. All values are given. Means question I will read, then you will understand. Okay, quickly will understand and you can solve also. Very easy. Okay. But if you will not understand, then this numerical only will become very difficult. Question is long because many data is required. Hence question will become long. Hence you have to understand and put the values simply and you will get the result. not a difficult. Even competition also same type of, because question is long, that is can't do anything, sir. Only this value, one value you have to calculate, other values they will give. Okay, either directly or indirectly they will give. Then question I am reading, the vapor pressure of pure solvent at a certain temperature is 0.850 bar. Here temperature is no role, but they have given, because it is experiment. Whatever numericals are given, that is the based on experiment. That's why they have written the vapor pressure of pure benzene. Vapor pressure of pure benzene C6H6 at a certain temperature is 0.850 bar. A non-volatile, non-electrolyte solid being 0.5 gram, when means weight they have given, solute weight is given, W2 weight is given, 0.5 gram is added. When added in 39 gram of benzene means molecular this weight of solvent they have given, W2 is given, W1, W2, 39 gram of benzene, and its molecular mass is also given 78 gram per mole, but it is a benzene. You can calculate also C6H6, it will come 78, but in question it is given. Vapor pressure of the solution, vapor pressure of solvent is also given. Benzene is solvent, it is given 0.850. Then now vapor pressure of the solution is also given, that is a 0.845 bar. What is the molar mass of the solute substance? You have to calculate. Then nothing is there. All values are given except molecular mass of solute, M2 you have to calculate. All values are there. Then P2 value is this, then P1 naught value is given 0.850, and P1 value is given, means vapor pressure of solvent in solution, that value is 0.845. Then now we put the value in formula, then you will get 0.850 minus 0.845, little less is there, divided by 0.850. That is this is the relative lowering of vapor pressure, and that is equal to, now except M2, molecular mass of solute, all things are given. W2 is given 0.5 gram. You write in the place of W2 0.5, and this benzene M1 you have to write molecular mass of solvent, upside M1 was there, then 78 you write, down M2 you want to calculate, and W1 means solvent weight is given 39. Then cross multiplication you can do. You will first to multiply all the things, and after that M2 value, after the cross multiplication you will get. Then you will get molecular M2 value means a solute. You will get, after solving, you will get 170 gram. 170 gram you will get per mole. This is the weight, that is called this thing's molecular mass. Molecular mass, and also just to add whatever molecular mass is there, weight, that is the per mole, and that is 170 you got. Now elevation of boiling point is there, but it will take but here I will tell you elevation of boiling point. I will tell you it is somewhat similar. I will finish it. Okay. Here main things I am telling you that elevation of boiling point. Elevation, second property is elevation of a boiling point. Here what will happen? Solution's boiling point will increase. Here, elevation of a boiling point. Here what will happen? Actually boiling point with this you have seen that non-electrolyte and non-electrolyte actually you are not using only non-volatile. You are not using only non-volatile, that should also be non-electrolyte. Non-electrolyte means it should not be electrolyte. You can't use ionic. Only glucose, fructose, this type of things you can use. It will not break into ions. This is again limitation of lowering vapor pressure. Okay, so lowering vapor pressure you can utilize, but here actually in numericals also I told you both terms are there, non-volatile, non-electrolyte. Okay, because if it will be electrolyte, then result will differ. That I will tell in the last. Okay, in the last, after discussing all four separate, I will discuss if this solid will be electrolyte, then what will happen? Value will change. Okay, that's why separately I will tell expression I will derive or I will tell you. Then here elevation of boiling point. Here you have to understand main things. I told you this is the elevation of boiling point of the solvent, because in solution mainly role is of solvent. In solution solvent is there. Then here what will happen? It is related to the lowering of vapor pressure. You will quickly understand. See here, you are if you will add a solute, then vapor pressure will decrease. Correct? Then now if vapor pressure will decrease, then how it will affect the boiling point? Boiling point definition you know. That boiling point is the temperature at which vapor pressure becomes equal, vapor pressure of solvent in solution becomes equal to the atmospheric pressure. That temperature is called boiling point. Boiling point is the temperature at which vapor pressure of solution you can't write. Somewhere in bigger sense it can consider, but correct is that the temperature at which vapor pressure of solvent in solution is equal to the or becomes equal to the atmospheric pressure. That temperature is called boiling point. Then here, because after adding the solid vapor, pure vapor is more vapor pressure. Then here, if pure vapor pressure is there, as for example water, then it will boil at 100 degrees centigrade. Exact is 100 degree centigrade it will boil. That time pressure will be vapor pressure, that time it will be 1.013 bar. Okay, leave it. Pressure first. With that 100 degree it will boil. 100 degree boil. At that time pressure will be 1.013 bar. This now you forget. Just to understand first that pure water boils at 100 degrees centigrade. But now if you add the solute, then vapor pressure will be less. then what will happen? For the pure solvent, vapor pressure was less. Pure solvent vapor pressure was more, not less, more. Then because it was very close to the atmosphere, this vapor pressure, pure solvent vapor pressure was very close to the atmospheric pressure, or sometimes you can tell equal. But now that time 100 degrees centigrade is required. Now as soon as you will add solute, then vapor pressure will decrease. And when vapor pressure will decrease, then now you have to heat more. Then more vapor from the solution, more solute vapor. If you will heat the solution, then more solvent of the solution will go to the vapor. Means vapor pressure you have to increase. Then you have to heat more. Vapor pressure now it is decreasing, but you have to bring vapor pressure equal to atmospheric pressure. Then you have to heat more. Then more solvent molecules will go to the vapor phase. Then it will become equal, vapor pressure will be equal to the atmospheric pressure. Then more temperature you are applying. That's why when it was pure, then 100 degree. But if you can say, if this you have added, then now you require more temperature to boil. Then this is called elevation. Boiling point increased. Correct? Then this is called elevation of boiling point of solvent in solution. Temperature increased. It may go more than 100 degree, maybe 100.1 degree or 100.2 degree. Simple example. Then now what is the difference of temperature? Then 102. Suppose 2 degree increased. 102 minus 100. That is called difference in boiling point. This is the difference of temperature. Suppose it was the a small b term is used for the boiling point. Then suppose TB is the boiling point. TB 0, zero script you write for the pure solvent. It is more, but temperature in the term, in the sense of temperature, boiling point. Now you can see how in mole fraction all things are dependent. Concept is the same, but boiling point is increasing. Then boiling point of pure solvent is boiling point is less pure solvent, and solution is becoming more. Then boiling point of solution is more and solvent is less. Understood? I am not talking about the vapor pressure. I am talking about the boiling point. Then for this, boiling point of pure solvent will be less. That you keep in mind. Boiling point of pure solvent is less than solution or solvent in solution. Okay, solution also you can tell, but correct thing is that solvent in solution. Both term used. Solvent in solution. Then that is the delta. That is actually called delta TV. Difference at 2 degree difference. That is called delta TV. Okay. Then this is the only important things. After that, all are the you can say formalities. Expression you will get. Now you know that I told you delta TV. That is the TB minus, TB is the more, solution's boiling point is more, then TB minus TB capital T, TB minus TB 0 means not, TB not, that is called delta TB, is known as elevation of boiling point. Experiment has been done. Then all things has come. Experiment have shown that dilute solutions, the elevation of boiling point is directly proportional to the molar concentration. Okay, molar concentration of the solute in a solution. Now it is clear by the concept that this delta Tv is directly proportional to a small m, molar concentration. Molar in kg, you will take in kg 1000 gram, already know number of moles present in 1 kg of solvent, that is a molar, LAL. Then by experiment it is shown that delta Tv is directly proportional to a small m, means solute. If solute will be more, then it will affect the boiling point. More the solute, then boiling point will increase. This is only for dilute solution. You can't make concentrated solution. Okay, otherwise it will not work. It is, these properties are only for dilute solution. Then it depends upon, directly depends upon m, but not for, you can make too much value of m. It is in the range of dilute solution only. In that way, directly proportional to m. Delta Tv is directly proportional to m. And you can equate it, equality, then some constant you have to multiply. Then now it will become delta Tv, that is equal to Kb, you multiply by constant Kb into m, Kb. Then now delta Tv is equal to Kb into m. Here a small m is the molality. Here m is the number of moles of solute dissolved in 1 kg of solvent, and the constant actually Kb, that is the proportionality constant, Kb, that is called boiling point constant. Kb is called boiling point elevation constant, Also another name is here molar elevation constant. And third is also there, ebullioscopic constant. Question may be asked in any way, what is the boiling point elevation constant? That is the one term. Second term, same, for the same Kb is three name. First name is the molar elevation constant. Second is the molar elevation. First is the boiling point constant, boiling point elevation constant, first term, and it is also known as molar elevation constant. And third, ebullioscopic constant, EBU, EBULLIOSCOPIC, ebullioscopic constant, EBU, ebullioscopic constant. Okay, this definition is also as what is the ebullioscopic constant. And Kb unit is Kelvin. K means Kelvin. Kb, what is its unit? Units they are asking in examination question. Then Kb has a Kelvin unit, K kg per mole. K, here K means Kelvin, K kg per mole. Remember, K kg per mole. K is here Kelvin. Value of Kb, actually for different you can say solvent, Kb value will be different. Each solvent has own Kb value. Okay. Now again now we have to correlate, because molality you have used, delta Tb is equal to now Kb into m. Then what is the value of m? Molality value you have to introduce. Molality, then molality already you know that molality is equal to means a small m. A small m is equal to that W2 divided by M2. Actually molality, mole Mole means what? Weight divided by molecular weight. Weight divided by molecular weight means here W2, suppose solute is 2, solute is 2, W2 by M2, that is the number of moles of solute. Then this number of moles of solute, W2 divided by M2, this is present in suppose W1 gram solvent, correct? W1 gram solvent. In W1 gram solvent, this mole is present, this number of mole is present, solute number of mole is present, that is the M is present. W gram solvent contains M gram of M mole of solute. M value you can put later on, W2 by M2, you keep later on. First M you consider. W1 gram solvent contains M moles. Then 1 gram how much? M divided by W1. Then in 1000 gram how much? Just multiply by 1000, means M into 1000 divided by W1. This is the main formula. Then this actually M value is this only. This is the M value. That is the M W2 into 1000 divided by M2 into W1. Now in this you have put the value of M value, that is equal to W2 by M2, that you have written here. 1000 is upside, down is W1. Solvent is in down and solute is upside, W2 into 1000. Okay, very easy calculation I have told you. Then this M is equal to now M value you got now 1000 into W2 divided by M2 into W1, correct? M2, capital M2. This is the value of M molality value you got. Then now this M value what you got now, you can keep here in delta TV, elevation in boiling point, that expression you got, Kb into M. Then now this M value, here you put the value of M, then that is the final expression. Means you will get, after putting the value, delta TV, that is equal to Kb. Already it was Kb in the formula. Now M value you are writing, that is the W2 into 1000 divided by M2 into W1. Then you got the relation, WTB is equal to Kb into 1000 into W2 divided by M2 into W1. Only you put the value of M. You have put the value of M. Then now delta T value you are knowing. Then after cross multiplication, here see, here delta TB is there, Kb value is a standard value. It will be given in examination. Okay. Then now mass of solute, mass of solvent and molecular mass. Three things are variable out of 5. 1000 already is there, no problem. Kb value will be given. Then now three values there: weight of solute, weight of solvent, and molecular mass of solvent. Here there is no role of molecular mass of solvent, because 1000 you have used in the place of that. Then out of this three term, W2, M2 and W1, any one you can calculate, provided out of these three, two are known, any one. Generally M2 you have to calculate by cross multiplication. If delta TV value is given, then another values are also given. M2 you can calculate by cross multiplication. Means M2 is equal to 1000 into W2 into Kb divided by delta Tb into W1. Means in the place of, in a simple way, how will you remember? Then what you, delta Tb expression you got, then you bring M2 to that place. Just interchange the place of delta Tb and M2. Okay. When easy way to, I will get it by cross multiplication, but simply I am telling you that in the place of delta Tb M2 you bring, or in the place of M2 delta Tb you bring. That's enough. Thus, in order to determine the M2, you should know the other values. 1000 is will be no 1000 is given, not required anything. Kb value will be given, W2 value will be given. If suppose delta Tb value is given and weight of solvent is given, means if all things are there, M2 you can calculate. Okay. Then 3 to 5 including delta Tb 6 are there. Then in that 2 will be not, this 2 are not problem. Kb value will given, 1000 is there. Then rest 3 things including delta B 4. If these are, if you can say out of these 4, 3 are known, 4th you can calculate. And this I have discussed. Now numerical is there, I will discuss in next class. And one more thing, sir, here by graph also you can understand solvent will, I told you solvent vapor pressure will be more. Solvent vapor pressure will be more, but boiling point will be less. In graph you can show. First you should one line you have to, actually vapor pressure versus temperature, that graph will be there. Vapor pressure versus temperature graph will be there. Then 2 line will you have to, 2 parallel line, and diagonally you have to draw, roughly diagonal. Then solvent will be upside, because solvent vapor pressure is more than solution, or you can say solvent vapor pressure in solution, that you have to down. First line you have to draw for solvent, parallel line, and down line will be solution. Then vapor pressure of solvent will be more, that you know, but boiling point of the solvent will be, pure solvent will be less, and solution will be more. Then upside also, if you are this x-axis temperature, y-axis pressure is there, then in parallel to the x-axis upside, when pressure is 1 atmospheric pressure, upside just you write 1 atm and one parallel line of parallel to the x-axis upside you draw. Then there you have to give 2 mark, one for solvent, other for the solvent in solution, that is the solution only. 2 mark you can give for boiling point. Then first solvent boiling point will be less, down you write as a these things for Tb 0, Tb 0 is for solvent boiling point is less. After that less you can give a gap of a little gap, a small gap, and then you boiling point is more, because this diagram is vapor pressure versus temperature. Then temperature is less for the solvent, pure solvent. Then that T1 not you write 1 point on the x-axis and little gap, and then temperature is more for the solution, then that will be Tb, that is for boiling point of solution, it is more, boiling point is more. Then like this parallel to the y-axis 2 line you draw, it should match to the up line, parallel to the x line you have drawn, there it should match. That will tell which is the now distance. You know that at boiling point, when boiling, then vapor pressure becomes equal, only that time liquid solution will boil. And what you will think here in graph, that boiling point is different. Boiling point of solvent is less and solution is more, but both will touch to the same atmospheric pressure. Both will touch to the one atmospheric pressure. Atmospheric pressure is 1. Okay. Then this, if you draw the line parallel to the y-axis, then what you will think that now vapor pressure of both solution and solvent are becoming equal, 1 atmospheric pressure. This I will try to send it this diagram also. Now I am stopping here. Thank you.